Hi, I'm Phil Durbin, and as Salil mentioned, I'm a community manager for OpenDP, and it's my pleasure to introduce to you Mike Shoemate and Andrew Vyrros, who are both developers on the OpenDP library. They're going to be talking about the library, its architecture, and roadmap for extension. And I'll just mention here at the top that we're happy to take questions at the end, but please feel free to go ahead and type into the group chat your question, and I'll be collecting them and asking Andy and Mike at the end. And with that, please take it away.
Okay, thanks, Phil. And hello, everyone. My name is Andy Vyrros. With me today is Mike Shoemate. We're software developers here at Harvard, and we're going to tell you about the OpenDP library. Here's a, sorry, I don't seem to be, there we go. A little bit of lag, sorry about that. Here's a preview of what to expect. We'll start out with an overview of the OpenDP library, what's in it, and what it can do. Then we'll get into some of the technical details, how it was constructed. Next, we'll give you a live demo of the library in action. And then after the demo, we'll come back and talk a little bit more about what's on the horizon for the OpenDP library. Now, I'm going to start by generating a little bit of drama because we're really excited about what we've built. It's been a long time in coming. Say hello to OpenDP 0.3. Okay, fair enough. It's a little odd that we're starting with version 0.3. So let's take a look at the timeline of the project to see how we got here. The progenitor of OpenDP was something called Smart Noise Core. And that was a partnership with Microsoft where we started exploring some of the ideas that would become the OpenDP library. And then next, we produced a series of prototypes for the architecture of OpenDP, working through things like data types and how we were going to do language bindings. Then over the summer, we did release a version 0.1, which was our first actual release. And that was usable for real work if you had some hand-holding from the team. Which brings us up to date, version 0.2.4, or actually 0.3, which is hot off the presses late last night. And that's what we're calling our first public release, as we've been hard at work adding documentation and examples and basically enough stuff so that people can get up to speed on their own. But I can't go any further without acknowledging the many people who helped us get here. Mike and I are the developers of the library, so we're the ones responsible for the architecture and the code. But we've had a ton of help from other folks. It's too many names to mention individually, but they've all moved things forward in different ways. We got a lot of input from other developers on the team, as well as great feedback from our fellows and interns. And the design we're implementing is based on a formal programming framework, which was itself guided by the OpenDP Design Committee. And then there are the great folks who keep the project and the community humming along. So heartfelt thanks to everybody here. Okay, so when we talk about OpenDP, you saw there are really a number of things that we might be referring to. So let me set some context for this presentation specifically. At the largest scale, what we're hoping to create is an ecosystem. We want to have a constellation of applications and tools, different privacy solutions powered by OpenDP. Then at the next level down is something we call the OpenDP Commons, which encompasses the software that OpenDP provides. It's sort of a collection of packages and tools that could be shared across many applications. And then finally, we get to the subject of this presentation, the OpenDP Library. And this is our core collection of embedded code. It's sort of the kernel that powers the rest of the ecosystem. So that's where the OpenDP Library fits into the big picture. Now let me explain what we're hoping to get out of it. What we're trying to create here is a trusted implementation of differential privacy algorithms. So something that can become the standard solution people reach for when they need to develop DP applications. So that's a bit of a lofty goal. So we're trying to approach it methodically. And we've identified a particular use case that we think has a lot of leverage. That is, we're focusing on generating summary statistics to be used when publishing releases of research data. And then we're building an architecture that works for that case and hopefully others in the future, something that's flexible, extensible, and verifiable. Now, as Professor Farnsworth says, this is just part of the OpenDP vision. The project as a whole is about making more data available for the public good. So it's important to keep that in mind, but this is a key part of that mission. So let's see how we can make a library that's flexible, extensible, and verifiable. First, I'm going to start with some building blocks. And these are the things, that structures that are at the heart of every OpenDP program. We have transformations, which you can think of as kind of fancy functions. They let us map from data sets to other data sets, or from data to data, or any of those combinations. And transformations let us do things like aggregation or conversion, or pretty much any kind of data computation. And common examples are things like sums and means, and et cetera. And then we have measurements. And these are also functions, but with some randomness involved. So they map data to any arbitrary value, or really a distribution of possible values. And measurements are about introducing noise to data for the purpose of privacy. And here you have the standard mechanisms of differential privacy, such as Laplace mechanism, Gaussian mechanism, and so on. Now with our building blocks, we want to be able to put them together in flexible ways. So that's where combinators come in. There's chaining, which lets us link some transformations and measurements together into a sequence, resulting in a single privatized output. We also have composition, which lets us apply multiple measurements to the same data, producing different privatized results. And then there's post-processing, which lets us take the privatized output of a measurement and then manipulate it in any arbitrary way. So these combinators, they make it possible for OpenDP to construct many different computations from a small set of primitives. That's our flexibility. Sorry, I'm hung up here. Okay, now I want to talk about extensibility, which relations help us with. And relations are a way of characterizing functions, particularly how much the outputs of a function can change given how much their inputs might change. That's a very abstract notion, so I'm going to try to build up to it with a little diagram. So first, imagine that I have a function Doesn't matter what the function does, just that it maps from some set, call it X, to some other set Y. Now I can apply that function to any particular X, and it'll give me an output Y. But what I'm really interested in is what happens with differing inputs. So let's say I perturb my X a little bit. Maybe I swap one record of the data set for another record, and I get an X prime. Then I could apply the same function again and get an altered Y prime. So this is what I'm interested in. I made some change to my input. What can I say about the corresponding change to my output? Let's try to be systematic about this. Say I choose some distance metric. Doesn't matter what it is, just as long as I can compute the distance between x's, two different x's. So I'll take any two inputs and calculate the distance between them. And then I'm gonna bound it below some value. That value is d in. That's my maximum distance between inputs. Now let's do the same thing. Sorry, I seem to be not advancing. Okay. So now let's do the same thing on the output side. I can choose another distance metric. Again, doesn't matter which one, as long as it can calculate a distance between y's. And I'll take the two outputs, do another distance calculation, and once again, set an upper bound. This one is d out, my maximum distance between outputs. So finally, we can see what a relation is, right? It's a way of relating distances between inputs and distances between outputs. So I take that upper bound on input distances, dn, and I take the upper bound on output distances, d out, and I relate them together by making a Boolean operation, which determines if a particular scenario holds for my function. And this is what relations are. They're, you can think of them as like a certification. And they say, if a relation is true for a given d in and d out, then you know that if my inputs are d in close, then the corresponding outputs are going to be d out close. Okay. So, why did I go through all that rigmarole? Well, this is how we get extensibility. In our framework, every transformation is certified by a stability relation, and every measurement has a privacy relation. And by doing things this way, we're able to generalize the notion of closeness that appears in the different definitions of differential privacy. So instead of having a fixed privacy loss that's associated with one particular static notion of privacy, we can incorporate any definition that we can write relations for. And then the really cool thing is that our combinators, they form a privacy calculus over these relations, such that when we construct new compound operations out of our building blocks, the privacy characteristics of the new operation can be automatically derived. This is one of the really elegant and powerful aspects of OpenDP, which we hope is going to allow the architecture to grow in the future. Yes, it's true that I'm absolutely not doing this subject justice. Fortunately, all the details are spelled out in the paper on our website, so please check that out. But hopefully, I'm giving you some flavor of how things work. Okay, so we had flexibility by combining building blocks, and we got extensibility via relations. What about verifiability? So let's do another diagram. Here's my silly little picture of a function. It's some code that computes the sum of a set of numbers. If I want a private version of that, I could tweak it a bit so that I clamp the input and add some calibrated noise and so on. That seems good, but how can I be sure that the code does what it's supposed to do? Well, the lovely thing about differential privacy is that it has a rigorous mathematical definition. I won't quiz you on it, but it's great to know it's there. We just need to make sure that our code lives up to it. So in OpenDP, we require that every module be accompanied by a mathematical proof. And the job of this proof is to demonstrate that the associated code lives up to the definition of differential privacy. This is a core principle of the OpenDP project, these proofs. So how does it look in practice? Well, let's imagine that we have some functions that we'd like to add to OpenDP. These take the form of code submissions, each of which has a mathematical proof attached. Then there's a process that we're building that takes in those submissions, inspects the proofs to make sure they're valid. It's only at this point that once everything has been validated, that we incorporate them into OpenDP, the library, and we can tag them as trusted functions. Yes, it's important to point out that the vetting process is manual, with human beings reading the proofs. Of course, it'd be great to leverage some kind of automated verification. That's something we'd like to explore in the future. But for now, we think we can get a lot of mileage from manual process. So that was pretty high level stuff. Let me talk a bit about the architecture of the system in the OpenDP library. And we built it with a layered architecture. Starting at the bottom, we have our core infrastructure, which is implemented in the language Rust, providing the common concepts of the library. Then based on that, there's a set of components, which are the implementations of the actual DP algorithms. And now if you're using Rust, you can build your applications directly on top of that interface, but we want to have broader adoption than that. So we've written a layer that exposes the library via the standard FFI, foreign function interface. That allows us to create Python bindings on top of the FFI layer for all our APIs. And this is what we expect most people to leverage, building OpenDP applications in Python. But there are many other languages out there, so we can potentially add bindings for them as well, allowing the creation of apps in those languages too. And then beyond language bindings, you could also imagine bigger systems, maybe targeting specific use cases like Microsoft Smart Noise SDK, which they're in the process of refactoring Smart Noise so that it's powered by OpenDP, which is a really exciting real-world validation of our work. Now, whenever I start mentioning languages, I tend to see people's hands go up. So I'll just anticipate some of your questions here. First of all, Rust, it's a little unconventional, but we've been quite happy with our choice there. The type system is very expressive, which lets us capture a lot of the constraints that we need at compile time. And the ownership model is powerful, so we can control where data is accessed. Rust is also great with FFI, which has made creating language bindings feasible. And also Rust has a great story for making cross-platform builds. which might seem like a minor technical point, but it saves a huge amount of maintenance effort. As for Python, we know it's not universal, but it does have a ton of momentum in many areas of data science, and it's been a great start for us. That said, we built the system with expansion in mind, and we hope to add other languages in the future. All right, I've been talking a lot, but I still haven't really said anything about what's inside the big box. Of course, there's a lot of love in that box, but in addition to love, there's a nice set of about 20 built-in functions. These are things like aggregations and simple statistics, plus various data manipulations, parsers, converters, and so on. We also have 4 core privacy mechanisms, Laplace, Gaussian, and so on. And then there are 3 core combinators for wiring everything together. It's just a starting point, and there will definitely be more, but we feel like it's already enough to build some nice real-world applications. Naturally, this wouldn't be a privacy presentation without some caveats, so I need to mention a few limitations of the OpenDP library. Namely, some of the privacy mechanisms, they're based on idealized math, but implemented with floating point numbers. And so that can cause issues in certain situations. We're working on shoring those up. And the affected mechanisms, they are tagged, but it's something to be aware of. It's also, I should point out the vetting process that I described, it's underway, meaning that some of the code and the proofs in the library, it's still being reviewed, and we'll be working on that in the future. And there are also some aspects of the framework paper that we haven't implemented yet, namely interactive measurements. And also one important practical note, our APIs, they're still subject to change. We've done a lot of iteration and things are relatively stable, but we need to preserve some flexibility. In due time, though, we'll declare a version 1.0, and that'll be kind of our stake in the ground for future stability and compatibility. At this point, I hope you're eager to give things a shot. If you want to try OpenDP, you can get it from all the usual locations. There's PyPy for Python, crates.io for Rust, GitHub if you want to dig into the sources. Pretty much anything that's at OpenDP will probably be there. But the one-liner is just pip install OpenDP, and you should be good to go. Okay, finally, I think we're ready for some demos. So I'm gonna hand things over to my partner in privacy, Mike Shoemate, who will show you the OpenDP library in action.
All right, hello. I've got 10 minutes of your time, so I'm going to use it. I'm going to use it well and go build some measurements. First off, I'm on the docs website, docs.opendp.org. There's a user guide here. There's also a developer guide if you're looking to contribute. I'm going to draw your attention to this section on transformation constructors and a section on measurement constructors. There are a listing of the building blocks available. You'll notice that the majority of the public API of the library consists of constructor functions. These are just functions that are used to build transformations and measurements with pre-approved vetted privacy properties. So I'll switch to the code. I've got a blank slate here. there's a one-to-one mapping between the transformation constructors, measurement constructors, documentation, and modules in the library at this time. So import, I should mention that my goal here is to make a bounded sum measurement. I'm going to import a clamper and a bounded sum. Clamp, make bounded sum. I'm also going to import a measurement. Make base geometric. It's a two-sided geometric distribution. And let's just make a clamp. So say clamp is equal to make clamp. And if you follow this definition down into the function itself, you get a lot of useful information, type hints, documentation, what errors it raises and assertions it makes. This is kind of the general pattern throughout the library. We don't want to waste your time. 0 to 10 is my bounds. And let's call it. Okay, so the library's already complained at us. Attempted to use a function that requires contrib. So notice that anything that's not made it through the vetting process is an explicit opt-in. So it'll tell you how to resolve this error, but I'm going to go ahead and just resolve it. OpenDP.mod. It's a lot of the administrative work happens in this. And we're going to enable contrib. And this should work. Okay, so it's able to make this clamp transformation. And let's go and do some things that transformations can do. So the two main things we're wanting to look at is checking the relations and invoking the clamper. So we're going to assert that clamp, when evaluated, input distance of 1 and then output distance of 1 is true. So we know that the clamp is a one stable transformation. Perturb any one individual in the input data set, you're going to have one perturbed record on the output at most. So this should pass. And we can also invoke transformations. So there's a nice shorthand here where you just call it. Pass some data in that will be clamped. I'll go -10, 5, and 20. And print that out. It does as advertised. One thing to keep in mind is that the data that you pass in needs to be a member of the input domain. And aside from that, we handle the rest of the process for you. There's utilities out there for checking these things, or at least there will be. So we've just made a clamp. I'm going to go ahead and make a bounded sum. Notice that the bounds here will have to be the same. We can only chain these computations if the output domain of the clamp is equivalent to the input domain of the bounded sum. We don't want the clamp to be emitting values that aren't viable inputs to this function. And the proof, the relation only holds if you're passing data in that's part of the input domain. So I'm going to pull these bounds out. I'm just using them both. I haven't actually made this computation chain yet. The typical shorthand here is just to use this right shift operator, and it builds a clamped bounded sum. We get similar features on the relation and the function invocation. In this case, the bounds are between 0 and 10. Their distances on the output are measured in terms of absolute distances, in terms of sensitivity. So the sensitivity on the output is going to be 10. And if I just evaluate that, you get as you'd expect. The sum is 15 after clamping. And let's make this private. So I'm going to use this make base geometric. When our chains start to get long, it's easy to break them up into multiple lines. I'll choose a scale that makes epsilon 1. I'll call this dp sum now. And epsilon will be 1. Just like that, we have a system that checks that the privacy expenditure of this measurement is 1 epsilon, and just evaluated a 1 dp release of our input data. So we've got some magic constants here, like 1 and 10. Either you know what epsilon you want, or you know the parameters you want. Let's say that we want to solve for an epsilon. We have a utility for that, just run a binary search. You'll notice that the output relation will pass for any value greater than 1. So we can just give it a large upper bound and let the library find the tightest privacy expenditure, or the minimum budget that still satisfies the relation. This is just going to be predicate function, the sum, and check it with input distance of 1, output distance of whatever we're searching over, and sum bounds. 0 and 100. This assertion is now unnecessary because the binary search will throw an error if it's unable to find a value that satisfies the requirements. No. Binary search comes from mod. And I'll also print out epsilon. So my first value in the output is going to be a bit loose because it's searching for this parameter for you. And then the second is obviously, the second output here is obviously the release. Now, in other situations, you might want to, you might have a budget and you want to find the scale, or you might have a budget and you want to find some thresholding parameter, or clip the tightest clipping bounds that still gives you an epsilon that satisfies your target requirements. In those cases, you can use other utilities like binary search chain to solve for this missing parameter, whatever parameter you need. And there's more examples of that in the documentation. So if I hop over here to the example section, there's some examples in the docs themselves, and it's kind of useful to go through those first because there's a lot of context in the documentation that isn't available in notebooks, but once you're ready, there's also notebooks. One great starting point is basic data analysis.ipynotebook. It goes over a lot of these things in more detail, like finding the search, like finding the scale parameter. So I think at that, I've covered what I want to cover. I'll leave it back to Andy. Thank you.
Andy, we can't hear you.
Sorry about that.
All set.
It's hard to find it in the when you're in screen share mode. So thanks a lot, Mike. I always enjoy seeing the library in action. It's a little silly, but it's very satisfying. And I also admire your bravery to do a live coding session. Where are we headed from here? Some things are pretty clear at this point. We know we'll be adding more statistical components and privacy mechanisms that will improve the options for building apps. We also want to make it easier to get data in and out of the system. And it looks like Apache Arrow is emerging as the preferred format there. I mentioned earlier that we're hoping to add more language bindings, and we've had some requests for R. And also, we really want to finish our implementation of interactive measurements, which are an important part of the conceptual framework. Looking further ahead, the picture gets a little cloudy, but we have some ambitions. Scalability, we know it's important for large data sets. So we'll be looking at ways to leverage external computation like SQL databases and frameworks like Apache Spark. We also know that differential privacy can bring special challenges when doing statistical inference. I think that came up in the keynote. And so we'd like to define a framework for thinking about utility in the context of DP. And I think that will be important for people to apply it to their domains. Beyond that, it starts getting a little harder to predict. We're interested in machine learning and federated learning, as is much of the world. And a number of folks have asked us about synthetic data generation, which could be very powerful. My personal interest and background is in local model differential privacy. So that's something I hope we can incorporate. But the bottom line here is that we're looking for your input, because that will help us figure out which direction to go. I hope we've stoked your enthusiasm. If so, we'd love to have your help. And there are many ways that you can get involved. Code contributions are welcome, but you do not need to be a software developer. We're also looking for feedback of all kinds, and testing is always welcome. Also, documentation is great because it helps the people who come after you. At the bottom is a link to our website that can get you started. And if you're interested in more info, there are more sessions on Thursday and Friday about contributing and what the process looks like. So you should definitely check those out. Okay, thanks for listening. It's been a real pleasure showing you the OpenDP library. I hope it will lead to some great applications and collaborations in the future. And with this, I guess we'll open it up to questions.
Yes, thanks. As I said, I've been collecting questions in the chat, and a lot of them have been answered already, which is great. I think what I might just do is share my screen. So Andy, I'm going to kick you out. Okay. There's another one. More questions coming in. So Damien, Salil, Mike, and Michael were having a long conversation about examples of a transformation, need the extensibility of stability relation provides. I'm not sure if this is maybe Salil or Mike, if you want to jump in and tell us if you feel like this has been answered sufficiently, if you want to go into this more, if you want to just continue the conversation in the doc. What are your thoughts on this one? Let's see. Oh, ask to I'm going to unmute Salil.
Yeah, I think this is probably one that's a little bit more in the weeds.
Okay.
That's better to keep offline.
Okay, great. Well, again, there's a link to this doc in the chat, so we can keep hammering on it and digging into those weeds more. And then a question about the FFI, Rust, interop, and Andy, I see you jumped in to answer this question about what about JVM languages like Java, Scala? Do you want to touch on this at all?
Yeah, I mean, we're basically trying to go for the broadest applicability possible. The lowest common denominator is a C FFI. Just about every language can talk to that. JVM is great, but and there are a number of languages that target it. But if you're not one of those languages, it really can be a challenge. So what we're doing is a bit more low level, but I think it gives us more targets possible, including Java.
Right. Makes sense. Salil, I think you jumped in on this question about smart noise versus OpenDP. Like, what are the major differences? Do you want to sort of summarize that here for us? Oh no.
Maybe Andy or Mike can follow up on that. Say more than I did.
Smart noise is a bit higher level. It's providing functionality that integrates with other platforms. This is OpenDP, the core library written in Rust, is very focused on building out relations and something that you can build on top of in other computing frameworks or other environments. Smart noise is one such environment that uses that foundation.
Great, thank you. Only 1 minute left, so we're trying to power through some of these. A question from Ryan: does the privacy calculus that was described accommodate approximate privacy definitions, some probable privacy failure?
So there's a base Gaussian measurement currently in the library that has an output metric, or has an output measure of smooth max divergence, where the distances are measured in terms of epsilons and deltas. And there's other extensions in, like there's currently an extension that Cyrus is going to talk about in the next presentation that extends it to FTP. And there's a lot of flexibility here for a lot of different definitions of privacy.
And this one was directed at, thank you, this is directed at Andy. Does the API do user level privacy scaling sensitivity by number of user contributions in addition to bounds?
Yeah, absolutely. I mean, it's up to you to sort of define what a user contribution is. The framework, that's when I was talking about relations and input distances, you can choose the input distance, say, between neighboring data sets, and that may be, you know, 1 user contribution or 5 or whatever you need it to be. So, and then that's accounted for in your sensitivity.
In my presentation, I used a clamp as the input, and the input metric for that is a symmetric distance, which is a measure between, you're providing an upper bound for distances between data sets, which encapsulates that use case.
Yeah, right. It can be both on the scale of the data and the scale of the, you know, contribution per user.
Great, we are over time. There are more questions in the doc. Maybe I'll just ask our speakers to take a look at that doc sometime later and circle back and try to answer some of those. Thank you so much. The presentations were great. A lot of great engagement with the community here. Thank you.
Thanks all.
We'll be back at 2:15 Eastern time.